Your Excellencies, distinguished guests, Professor Kim Sang-yu, ladies and gentlemen, it's a very, very great pleasure and honor to be with you today and to be able to address you. But when I'm talking to you here, I want to bring you a little bit up in the helicopter and think about, why are we really here? Why are we talking about green growth? Why are we talking about changing our energy systems? I believe it's because humanity is realizing that we need to manage our relationship with the planet as a whole. Our ancestors realized when they stopped moving around to catch their food, they realized that they needed to be able they had to manage their resources locally because the water was getting polluted from their own bodily wastes and so on. Then we realized we needed to manage regionally, and now I believe we're realizing we need to manage globally. That phase, I think, started when we went out into space and were able to take pictures like this. I know you've seen this picture because it's been the most downloaded from the net. But there's one thing about this picture that you haven't really worried about or thought about very much. And that's the fact there's no umbilical cord. Of course there's no umbilical cord. What is she talking about? The fact that there's no umbilical cord means that when we've used the resources that we get rich on, and make no mistake, we don't get rich from money. Money is a proxy for natural resources. When we have used the natural resources to get rich, when we've used them all, we won't get any more. We also can never really throw anything away. The whole climate change discussion is about waste products that are accumulating around us, waste products in the form of greenhouse gases. But it's not only from pictures like this that we're realizing where we are. Science has also been moving forward since we took these pictures. And we now realize that the Earth behaves as a system where physical, chemical, human, and biological components interact. That seems quite obvious, but until very recently, we drew the Earth and all of its processes, and then on the side, we drew people and made an arrow going into the Earth. No, the humans are not outside the system. We're a part of the system. And not only are we a part of the system, but we realize that our activities are influencing the state of the planet as a whole and at the global level. Now, often we think of this in terms of climate, but it's not only about climate. If you look at these red figures here on the left-hand side of the picture, they all start in 1750 and they all end in 2010, and they all tell something about the human endeavor. We have world population, world GDP, direct foreign investment, people living in cities, use of energy, use of fertilizers, damming of large rivers, water use, paper production, transportation, telecommunication, and international tourism. You can see there's been a tremendous increase since the 1950s, which is the dotted line here. We call this the Great Acceleration. It is partly because we are more people, but it is mostly because we've become richer. If we go over to the planet as a whole, we can draw pictures in the same way. From 1750 to 2010, the top three show you 3 different greenhouse gases. Then you have the ozone hole, you have the temperature of the Earth at its surface, you have ocean acidification. In the third row, you have fish capture, wild fish from oceans. Then you have shrimp aquaculture. Then you have coastal nitrogen, oxygen depletion in coastal waters because of runoff of coastal nitrogen from the coasts. Tropical rainforests, felling of tropical rainforests. And the middle one in the bottom line is very interesting. It's the conversion of wild nature to farmland. At the moment, we have about half of the ice-free area of the Earth is used for agriculture, and most of that for meat. We have an area that is the equivalent of North and South America combined that is used for grazing meat or for raising food to graze meat. And in the last one, we have the loss of biodiversity on land. We don't even know what's happening in the ocean. If we look at all of the vertebrates, all of the animals with backbones on this planet, that is to say fish, reptiles, amphibians, mammals, and we could put them all on a weight, on a scale, we would find that about 65% of the weight would be the animals that we produce to eat. About 32% would be us, humans, and less than 3% of the weight would be wild nature. Now, for climate, our politicians have said 2 degrees. That's the limit. We're going to let human-caused global warming be only 2 degrees. So we have a limit there. But I got together with a number of you can see a large number of international scientists. We're a large group working on it that have been saying, well, what about all the other things? It's not just climate we're influencing. Is there a limit to how much we can impact some of these other processes in the Earth system without, when we go over that limit, we run a risk of changing the Earth in such a way that humanity cannot thrive. And we arrive at the conclusion that yes, there are 9 different things, and we also, for 7 of them, identify what we think are limits for this is the planetary boundary, we call it. I hate the fact we called it boundary because people think thresholds. It's really more like blood pressure. If your blood pressure is over 120/80, it's no guarantee you're going to have a heart attack, but it increases the risk. Now we believe, we were unable for the tiny particles we've been talking about today in the atmosphere and for pollution, novel entities here, because these processes are so new, we can't go back and look how the Earth system has functioned in its history with relation to these processes. But for all of the others, we set a planetary, or proposed a planetary boundary. We also believe we're on the wrong side for climate, we're on the wrong side for biodiversity, which I call biosphere integrity here because that simply means how much have we disrupted life on Earth. For felling of forests, we're on the wrong side, and for the release of reactive nitrogen and phosphorus. But the point I want to use here in this talk is the fact that we arrived at the conclusion that the 2 most important things are climate and biodiversity. Well, we all know climate's important, but why biodiversity? Well, think about it. What's different about this planet compared to every other? It's the fact that we have life. Every planet has a climate because that's how much energy do you get from the sun, how is it stored, how does it move around, and what does it react with. Every planet has Lego blocks, if you will, elements and molecules that comprise the planet. But on most planets, those Lego blocks don't react with anything. They tell me Neil Armstrong's footprint can still be seen on the moon. That would not happen on Earth. And it would not happen because we have biology. And biology goes in and it transforms and it transports these Lego blocks. And every time it's been possible to get enough free energy to live out, then an organism or an organism group has evolved to do that process here on Earth. And at any given time in the Earth's history, the status of our environment, the state of our environment, is a product of the co-evolution of climate, which is a physical system of getting energy in from the sun, and of biology. Why do we have oxygen in the atmosphere? Thank you very much, biology. Why do we have an ozone layer? Thank you very much, biology. Why do we have coal, oil, and gas? Because when green plants evolved, the bacteria that could break lignin down, the green plants hadn't evolved yet. So you got a whole lot of plant material that was buried and ultimately became coal, oil, and gas. The reason that we're interested in all of the other things I mentioned in the planetary boundaries is that they operate either through life, through biodiversity, or through climate. So the message is that we cannot predict future states of the Earth system and where we're going without considering biological function or biodiversity. And I was involved in a paper this summer, which I believe is my ticket to being here, in which we went in and said, well, now that's very good that our politicians went to Paris and they said, we're going to stop this at 2 degrees. And we're going to manage this by, we have a button. We have a button for our emissions, and we're going to turn that button. And when we turn it up far enough, the Earth will be 2 degrees warmer, and he assumed that the Earth will stay at 2 degrees warmer. The problem is, if you study the Earth as a system and look back at its history, you realize the Earth has never had a period of time when its temperature was about 2 degrees, or a longer period of stable time when its temperature was about 2 degrees above the pre-industrial. If you look at the last 400,000 years, you can see the temperature here in red, and this is the temperature in red, and these are ice ages that come and go. We evolved here about 250,000 years ago, and biologically we were as we are today. There was no reason why we couldn't have developed new or modern civilizations in all of this period here, but we didn't. We didn't do it until right here. And all of the other, there were, by the way, about 10 other species of humans, and they all went extinct in this period. But everything we associate with modern humanity, that is to say agriculture, written language, Bronze Age, Stone Age, everything, it's all in this little period here when the climate has been basically as it is now, relatively warm and very, very stable. So we know for certain that humanity can thrive here. We don't know we can thrive in any other state, so it would be very dangerous and silly of us to do something that could change that state. Are we changing that state? Well, yes, of course we are. You all know this figure. It shows the change in temperature since the 1880s until 2020, or until now. If you look at it on the scale of the last 2,000 years, you can see that the temperature was actually, until very recently, getting just a little bit colder. In fact, some scientists think our warming has avoided the next ice age. The rate of change at the moment where it's getting warm is about 170 times the rate of change prior to the last 100 years, or since 1970. It's about 170 times higher than it was. And it used to be going down. Now it's going up. And the rate is 170 times greater than the rate with which it was going down. And the rate of atmospheric CO2 increase over the last 20 years is about 100 times the maximum sustained during the last deglaciation, about 21,000 years ago. We all know the IPCC's projections. Well, we can put the IPCC's projections in on this picture that we saw a little while ago, and we see we are in a position where we are vastly changing the state of the Earth. We are committed to something between 1.5 or 2 degrees. If we stopped all of our emissions right this minute, we would still reach 1.5 to 2 degrees above the pre-industrial. If we get up here to 4 or 5 degrees, the Earth will essentially be, we will not recognize it, and our societies may well collapse. In this middle area, where I guess we're going to land, we have something called tipping points we know that are out there. Tipping points, what are they? Well, they are processes in the system. For example, all the melting of the ice on Greenland, or the felling of, or the removal of the Amazon rainforest, where we know in the Earth's history that these things have happened and that they have changed the climate. And if we look at them individually, we can see they are all changing. Some of them are beginning to move. So we know they are in motion at the moment. We also looked at all of the things that would happen. In addition, if we turn that knob up to 2 degrees, what else is going to happen out there? And it turns out permafrost thawing. If you go through all the literature, it says that you get something between 0.5 and 0.16 degrees, average 0.9 degree by 2100. We don't think that release of methane from methane hydrates will really happen. This weakening of land and biological carbon sink, by the biological carbon sinks in land and in the ocean, increased bacterial respiration in the ocean, Amazon forest dieback that we're seeing, boreal dieback feeding. we arrive at the conclusion that in the worst case, I mean, there'll be a range, but in worst case, almost a degree more of temperature increase. If we turn the button to 2 degrees, almost a degree more from the biological and other processes in the system. If we go back to those tipping points, we know that science says that the yellow ones are likely to go at between 1 and 3 degrees temperature rise. We're already seeing them moving. So if we go to 2, if we make 2, and remember what the countries have offered to do actually wouldn't make it to 2. It would bring us to 3.3. But if we could make 2, then biology and so on are going to bring us possibly up to almost 3. And we have some of these tipping points that will go from 1 to 3, which could then trigger ones that will go from 3 to 5 degrees, which could then trigger the ones that will go at over 5 degrees. And all of these will influence climate the wrong way. They will warm the planet. Why in that? So basically, we're arguing that we could be that we could set a chain reaction going if we bring it up to 2 degrees. So basically, we're saying that there was this period down here where the Earth is cold, but it can also have a period when it's warm, and we know it's been this warm. We know it's been this warm before. So the Earth, and what we're suggesting, politicians are saying we should stop right here. Well, it doesn't look to us like that's going to be very likely to happen. If you look at these warmer periods that we had before, you can see that the Eemian, which is about 125,000 years ago, had much lower CO2 concentrations than we have today. It was 1 to 1.5 degrees warmer than the pre-industrial, and 6 to 9 meters of sea level rise. If you go to the mid-Pliocene, which is 3 to 4 million years ago, CO2 levels such as what we have now, 2 to 3 degrees warmer, and 2 to 22 degrees meters more of sea level. And if you go to the mid-Miocene, you find again CO2 concentrations as we have now, and sea level rises of 10 to 60 meters and 4 to 5 degrees warmer. So how plausible is this? Well, we know that the behavior that we're suggesting that would bring us to what we're calling Hothouse Earth is similar to what the Earth has been doing since the last ice age. We know that Hothouse Earth conditions are accessible with the CO2 concentrations that we have now and that we're looking for at the future. And we know that the feedback processes have all been in action before, and we know that some of the tipping points are already beginning to move. So our hypothesis is, we have 2 hypotheses. The first is that there are intrinsic biosphere dynamics. It's the biology we've been forgetting, guys, but intrinsic biosphere dynamics that could shift the Earth system to a hot, ice-free state, even if we control and keep our release of CO2 at a level that would supposedly keep us at 2 degrees. But we have a second hypothesis, and that is that when we understand these processes and feedbacks as well as we do, that it will be possible for us to manage our relationship with the system as a whole in such a way as to keep the temperature at about 2 degrees above pre-industrial, and in that manner essentially keep the conditions that we have today. What can we do? Well, of course we can reduce greenhouse gas emissions. We can also enhance or create negative feedbacks. I mean, we can plant trees. We can hopefully get to the position that we can capture carbon and store it. We could modify the Earth's energy balance by reflecting some of the sun. We wouldn't get rid of ocean acidification and so on, but these are all things we could do. This is what's in the toolbox. We could slow or reverse population growth. And remember, when we have that discussion, it's not just about how many babies are being born. It's about some of us who aren't respecting our expiration date. So it's about being born, and it's also about not dying. We could change our consumptive behavior. We could eat less meat. We could improve and change our governance. We need value changes in our society that actually move toward this stewardship of the planet. Technical innovation is also important, and we should emphasize that here at KAIST. and we need to build resilience in our societies for transformation. So this is not just about changing our energy system and reducing our CO2. What will the future trajectory of the Earth system be? I don't know, but I do know it will be a function of how we manage our relationship with the rest of the Earth system. Thank you.
Thank you again for the meaningful lecture, Professor. With this, we end the opening plenary of the 5th Annual Seoul Climate Energy Conference 2018. Thank you very much again for your participation. Thank you. And ladies and gentlemen, let me make some brief announcements. From now on, we will have a break for 10 minutes, so please come back to the hall by 11:10. Thank you. Also, during the break, please feel free to stop by at Dynasty Hall Room 3 for research poster session. This unique side